today, Madison May with the USGS will be presenting her research on water resource monitoring in the Puʻuwaʻawaʻa unit of the Hawaii Experimental Tropical Forest. Her research is being done through the permit with the HETF, and please note that permits are required when entering the HETF for research purposes. Madison, whenever you're ready, you can start.
Yeah, let me get my screen share up. All right, does that look good on your end, Olivia?
Everything looks good.
All right. Well, thank you everyone for joining today. I'll go ahead and jump right into it. So the current water resource monitoring that we are doing in the Hawaii Experimental Tropical Forest is an operation of the Kīholo rain gauge. But before I go into details on the rain gauge, I wanted to start out with a brief overview of our broader USGS monitoring program, give some information about how rain gauges work, show you guys how to find and access our USGS water data online, some considerations for anyone that's using provisional real-time data, and then finally we'll close out on the importance of the Kīholo rain gauge data and some examples of how it's being used. So for those of you that may not be too familiar with the USGS, our mission statement is to serve the nation by providing reliable scientific information to describe and understand the Earth, minimize loss of life and property from natural disasters, manage water, biological, energy, and mineral resources, and enhance and protect our quality of life. Some of you that are based on Big Island may be familiar with our sister USGS offices, the Pacific Island Ecological Research Center. I know I saw Gordon Tribble from Pierce on the call today. And there's also the Hawaiian Volcanoes Observatory. So there are a lot of different types of USGS offices within our Pacific Island Water Science Center office. We are primarily focused on monitoring the quantity and quality of surface and groundwater. We've been monitoring water resources in Hawaii for over 100 years, and the water monitoring program was focused primarily on surface water. So in 1909, there were 12 streams that were gauged continuously. Just 5 years later, in 1914, this had a big expansion. We had 87 continuous record streamflow stations. The size of our monitoring network has varied over the years, and we've even expanded to US-affiliated Pacific Islands. Currently, our monitoring program encompasses about 350 different types of sites across Hawaii and Guam. So some of the images up in the top right, you'll see one of our technicians servicing a rain gauge on Oahu, got a technician doing some surveying at a station on Guam. And in the bottom right, one of our technicians measuring the stream flow on Wainiha River over on Kauai. Data from all of these sites are publicly available and are utilized by a variety of different people, including reservoir operators and designers, water managers, emergency management personnel, researchers, city planners, engineers, recreational users, and many more. In order for us to operate and maintain this network, we rely on some federally appropriated funds from the USGS, but also on funding from many federal, state, and private cooperators. Where and why we have stations in particular locations largely depends on the cooperator's need and uses for the data. So that's kind of a very brief and condensed overview of our monitoring network. Now I'm going to get into some specifics on rain gauges and finish out talking about our Kīholo rain gauge that's part of that network. This slide is showing a couple different standard types of rain gauges that are used by the USGS and other agencies. There are other more sophisticated models and methods, but I'm just going to be talking about a brief overview on these three with more focus in the coming slides on the primary type of rain gauge that our office uses. So the first photo on the left, this standard rain gauge, any of those small graduated cylinders that some of you guys might have in your backyards or you may have seen would be considered the same type of rain gauge. And this is a very rudimentary method, but it can still provide very accurate rainfall records of rainfall totals. The rain is simply captured into the accumulation can or a graduated cylinder, and then a person has to physically be on site to measure and read the depth of water in the collector. Sorry, moved on me. Person physically has to be on site to measure that depth of water and then empty it out routinely. So this method is advantageous when the total rainfall amounts are of interest, but it cannot provide rainfall intensity rates or real-time data as a standalone. It's also important to note that you can get evaporation between visits and measuring of these cans, which could bias your total rainfall amount low. However, these standard rain gauges can be supplemented with automated electronic sensors that are installed in the can, and that way they can provide an automatic and continuous measure of the water level and hence rainfall totals and intensity rate calculations. A person would still have to go to the site routinely to empty out the accumulation can though. So moving on to the second method shown in the middle, the tipping bucket counter or TBC gauge. This is the primary type of rain gauge that we operate. And on the next slide, I'll have a little bit more details about how they work. But it allows for us to provide real-time rainfall totals and intensity calculations. And it does not require any dumping or emptying out of a catchment. At some sites, we utilize a tipping bucket rain gauge with a standard rain gauge as a comparison check, or we might operate two independent tipping bucket gauges at the same location to provide a real-time comparison check. And then the image on the right is a relatively new type of precipitation gauge that our office is beginning to explore, and it's a weighing rain gauge. As the name sounds, this method physically weighs the amount of precipitation that falls into the catchments and can provide highly accurate real-time precipitation totals and intensity rates for both rainfall and snow. Some of these models even have a heater that can melt any snow that falls into it. But similar to the standard rain gauges, someone would still have to be on site to routinely dump and empty out that can and that catchment before it overtops. So moving on to some more details about how those tipping bucket counter rain gauges work. The image on the left is showing what's a pretty standard tipping bucket gauge. Most have either an 8-inch or a 7.87-inch diameter catchment size, so just the diameter going across the top. Different models of TBCs can measure different rainfall intensities. And in Hawaii, because of the high rainfall rates we get, we typically use models that can measure up to at least 27.6 inches per hour. This middle image is just kind of showing a cutout of that housing, so you can see water flowing in. And then this image on the right is what's on the base of that housing. So as rain falls down and enters into that collector, it passes through this fine mesh screening that's going to filter out any debris that might be in there, so that as it flows through this tiny nozzle, only the rainfall is dripping down. And that's going down into the interior of the housing. As the rain flows in through the interior of the housing, it falls into these small buckets. And the rain will start to fill that bucket up, and it'll slowly start to tip over right before it reached its calibrated amounts, so that as it's tipping, it'll continue to catch those last few droplets. In the USGS, the standard bucket size that we use is a 0.01-inch bucket. So one bucket tip equates to 0.01 inches of rainfall. After one of those buckets is tipped, the other bucket on the opposite side is already starting to fill up, and that process just continues with the buckets tipping back and forth with each 0.01 inches of rainfall. The water is draining down into some holes at the base of the housing unit, so it's not anything that we've got to empty out routinely, which is the nice thing about these ones. The magnet and reed switch mechanism allow for us to determine when each of those buckets are tipping. It's essentially just closing an electronic circuit as the magnet passes by the reed switch with each bucket tip. Those circuit closures are detected by our data logger, which is essentially just a small computer. So it's recording each time that bucket tips and each 0.01 inches of rainfall, and then transmitting that data back to our office. And then a couple other things I'll point out on this image is we've got a bubble level on the tipping bucket gauges. Obviously, if that unit were not very level, then the buckets wouldn't be tipping when they should be with the calibrated volume of water, be tipping more so by gravity. And then they also have these calibration screws, which are going to help determine when that bucket's tipping. Part of our quality assurance that I'll get into on the next slide, we know that the bucket should tip once there's a certain volume of water in it. And if that bucket is tipping too soon, that would mean that the calibration screw on the opposite side was too high. And if we tighten that screw down, which would lower it, then it would allow more water to fill up in the opposite bucket before it starts to tip. So, and I'll get into a little bit more details about our QA and QC procedures here. In general, all types of rain gauges need to be sited in an area free from trees and buildings as much as possible, as they may obstruct wind-driven rain or alter the amount of rain collected due to erratic turbulence. Generally, you want the distance from an obstruction to be at least equal to or greater than the height of that obstruction. So in this image, I've got a tree nearby that's 20 feet tall. We want to make sure that we site our rain gauge at least 20 feet, if not further, away from that obstruction. That way we have an open 45-degree cone of clearance above our rain gauge collector. We also want to make sure that the top of the rain gauge is not mounted too close to any horizontal surfaces, because this could result in splash up into the collector. So if your rain gauge was flush with the ground or flush with a roof of some sort, you'd be getting rain from the sky and rain bouncing off of that horizontal surface. So they need to be at least a foot off of any horizontal surface as well. And then you want to make sure your mount that your rain gauge is on, especially for a tipping bucket, is very stable and solid. So you can imagine if this tipping bucket gauge mounted on a pipe wasn't very sturdy and it's able to move around in the winds, that wind shaking the pipe would allow those buckets to tip back and forth and falsely register precipitation tips. So we do regular and routine quality assurance checks at all of our rain gauges. About every 2 months, we'll go to the site and make some visual observations to make sure that cone of clearance is open and clear and free of obstructions. We'll check the collector and the funnel and the screen to make sure that they're free of debris. And we also check to make sure the unit is level and the mount is secure. We'll make a comparison of the total rainfall collected between our visits. And that may be between our primary and our backup TBCs that are at the site, or it could be between a primary TBC gauge and an accumulation can, a standard rain gauge that we've got at the site separately for a check. The last thing we do during routine quality assurance checks are what we call tip tests. In these tip tests, we remove that housing and we manually tip those buckets back and forth a total of 30 times. And then we check to see in our data collector that it registered 0.3 inches of rain. If you recall, one tip is 0.01 inches, so 30 tips should register 0.3 inches in our data collector. So those are just like the basic checks that we do during every single visit. But then annually, we do a little bit more quality assurance checks on them with calibration tests. We take a known volume of water and we pour it through a small nozzle. And this allows us to simulate a certain amount and rate of rainfall. Then we take the expected value from that calibration kit and compare that to the registered value in our data logger. If the differences are greater than 5%, then we make adjustments to that unit, maybe by adjusting those calibration screws, or we might have to replace that unit if it was in really bad condition, and recalibrate it after we've made those adjustments to make sure that it's within 5%. We may do these calibration checks more frequently than annually if those comparison checks aren't yielding favorable results, or if there's any indication that the TBC may be in error. So that kind of covers a brief overview of rain gauges and how they work. And now I'm going to talk about what kind of data we have available on the internet for public to access. We have stream stage and flow, reservoir stage, rainfall, groundwater levels, water temperature, turbidity, suspended sediment, specific conductance, and many other types of water quality samples. You can see in the top right image, these are the 10 sites that we have with real-time data on the island of Hawaii. And across the whole state, we have about 107 stations with real-time data. And then of course, we have thousands of historical stations that we may have collected data at for some point in time that's still available online, or we may have sites that are not necessarily real-time data, but we're collecting information and that's available to the public once our technicians visit the sites and upload the data into our database. So now moving on to how do I find that data? Well, if you can remember this URL, which I think Olivia is going to share after the presentation, that'll take you to our Pacific Island Water Science Center homepage. Down on the right side, you'll see a link to our current real-time conditions page. If you can't remember that URL or you lost it for some reason, you can also just Google USGS Water Hawaii, and that'll take you to our current conditions page. One of the first links will show current water data for Hawaii. Both of those, whether you choose the current conditions page from our homepage or Google it, will take you to our National Water Information System web interface, which is called NWIS Web. On this page, there's a lot of different options for viewing different types of water data. You can see the hot links on the side for stream flow, precipitation, reservoir, groundwater levels. In this example, I've shown selecting all current condition sites. And that brings us to another page with a table of all of our real-time sites is showing 122 because it's including our Guam sites as well. And you can view these stations showing up on a map by clicking Show Sites on a Map. Or if you know the site name you're interested in, you can find that in the table. In this case, the Kīholo rain gauge. We click on the station number, which is just a site-specific number for that location. And that'll bring you to a page specific for that site with plots of the data for the last 7 days. And you can go back in time and view previous data and download that data. So now I want to point out some considerations for people using and looking at our provisional real-time data, in particular our real-time rain gauge data. We do check our data and review them to ensure accuracy and eliminate potential errors from plugging of the funnel by debris and droppings, electronic interference or telemetry issues. And there may be failure of the electronic components like the reed switch or vandalism. And in the coming slides, I'll have some examples of what some of those data issues look like. So our recent provisional data are evaluated every weekday morning by our staff for these types of potential issues. And any data that's considered to have issues are either removed or hidden until they can be corrected. So in this picture on the right, we noticed there were some issues with our rain gauge on Guam. And so we applied this equipment malfunction qualifier so that we were not publishing data that we knew to be in error to the public. And then once something like that happens, our technicians go to the site, they make calibration measurements and adjust data if necessary, and thoroughly analyze that period of data. That gets sent on to a secondary experienced scientist to review the data, who will then approve that data when the record is determined to be accurate. So if you see in the bottom image, first half of this plot has this green banner underneath, which is signifying that this is a period of approved data that has gone through that review process and has been thoroughly quality assured. Whereas the period with the pink banner is considered provisional data, which is subject to change, may be subject to changing. So always caution yourself if you're wanting to use any of our data online for research purposes, make sure you're looking at approved data. And after that second level approval, all of our sites get sent to a third independent senior scientist once a year to review again and just make sure nothing slipped through the cracks. So here I've got some examples of some data quality issues on the next few slides. This one is showing plugging of the funnel. So as I mentioned earlier, most of our rain gauge sites, we operate an independent backup TBC or backup rain gauge, along with our primary rain gauge to provide real-time comparison checks for quality assurance purposes. We only publish one of these data sets to the public, but we can switch back and forth and switch over to the backup if we notice that the public or the primary rain gauge is having issues. So the image on the left is a pretty standard plot for a rain gauge for a cumulative rainfall time series. It almost has like a staircase appearance where you get a rain event and then it stops raining, get another rain event and it stops raining. So this is a pretty standard image for a cumulative rain gauge plot. The image on the right, however, appears to be having issues with the plugged funnel. The plot's indicating a pretty gradual and persistent rainfall occurring over about a week-long time period compared to the other TBC that was at the site. Sorry. This is pretty obvious to be a plugging issue. It's kind of similar to if your bathroom sink drain were plugged up with hair and things, all that water would just be sitting in the sink and slowly draining out. And so that's what's happening with the image on the right. Something had plugged up that funnel and that screen to where the water is just sitting in the collector and slowly draining out. And so we're not seeing the rain events occur in real time on this plot as they should be. So when we noticed that was happening on our primary rain gauge, we were able to switch over to the backup rain gauge for our public data set. And the other thing to note is you'll see the total for this was around 1.3 inches over this time period compared to the primary, which had a little bit over 2 inches. So the other thing, while that water's sitting in the collector, there's probably some evaporation occurring as well. So anytime we notice these issues, if we've got a reliable backup to switch over to, we will, and we'll get out to the site as soon as possible to get the rain gauge repaired and recalibrated. This image is showing a telemetry issue that happened at one of our rain gauges. There was a day where it recorded 12.84 inches of rain in about 15 minutes. This is very unlikely because if you recall, 0.01 inches is one tip of that bucket. So 12.84 inches would be 1,284 tips in 15 minutes. You break that down, that would be about 85.6 tips every minute, or more than one tip every second. So that tipping bucket was just going like doo-doo-doo. And this was very unlikely considering our nearby rain gauges only recorded about 0.2 to 0.4 inches over an hour time period around that time. When we pulled up and reviewed the raw transmission strand from that site, we noticed a bad character in that transmission strand that had been decoded into an incorrect rainfall amount. We were able to remove this erroneous data point and adjust the time series back down to where it should be after we noticed that. And then the last example I have of a data issue is electronic component failure. So you'll notice we have our primary TBC on the left and our backup TBC on the right. Between August 24th and 26th, the rainfall totals on our backup were about half the amounts from our primary. And then the issue continued to get worse as you look into August 30th through September 1st. There were a few rainfall events that didn't register at all on our backup. And this was because that read switch mechanism had failed. And so it was no longer sending that signal to our data collector indicating that the tips were occurring. So in this case, our backup was wrong, but we were still publishing our primary gauge. So it allowed us a little bit of time to get out there to fix the backup gauge while we were still able to use our primary gauge during that time period. So now I'm going to move into details on our Kīholo gauge and how that fits into our overall monitoring program. Last year, in cooperation with the State of Hawaii Commission on Water Resource Management and in collaboration with the University of Hawaii Resources Research Center, the USGS developed a water resource monitoring program. This program was intended to meet state needs for water resource assessment, management, and protection in Hawaii. Current and foreseeable issues related to water resource management and climate change effects were identified in collaboration with the Commission on Water Resource Management, the Water Resources Research Center, county water departments, and other stakeholders. These issues were used to develop a set of criteria for evaluating data collection sites for the monitoring program and a set of goals the program should achieve. So all the data collection sites were divided into two different types of networks. The first one being a resource management network to determine effects of water and land use change on surface water and groundwater resources. And then the other type of network was a climate response network to determine effects of climate change on surface water and groundwater resources in representative hydrogeologic settings. Using this framework, we took our current data collection sites operated in Hawaii and evaluated them and determined additional data collection sites to supplement our current monitoring program. The key findings from this report indicated a significant need to expand the current monitoring network, particularly in areas with critical habitats such as the Kīholo aquifer located within the Puʻuwaʻawaʻa unit of the HETF. So this is a figure from the statewide monitoring needs report, and it's showing the network of active rain gauges across Big Island. And I'll note that this network encompasses rain gauges operated by both the USGS and a number of other federal, state, and local entities. For a small mountainous island, the World Meteorological Organization recommends a network density of 1 rain gauge per 9.65 square miles. So on this image, all the darker green little diamond shapes are showing where there's an existing rain gauge. And that lighter green shading is showing that 9.65 square mile buffer area around it. So numerically, it looks like there's a lot of rain gauges on Big Island, but the network density is very low for the size of the island. There's only about 1 rain gauge per every 30.2 square miles, which is about 1/5 of the land area with rain gauge coverage. And in fact, Big Island has the least coverage of rain gauges per unit area out of the 6 largest islands in Hawaii, except for Lanai. So out of the 173 additional rain gauges that were identified in the report to add to our statewide monitoring program, more than half the sites selected were for Hawai'i Island, as the high spatial and temporal variations in rainfall make it the most underrepresented islands with current rainfall coverage. In the Kīholo aquifer in particular, there are only 7 active rain gauges, including our USGS rain gauge. But out of this 147 square mile area, that equates to only 1 gauge per 21 square miles, which is still not meeting the World Meteorological Organization recommendation of 1 gauge every 9.65 square miles. So this slide has shown some details on our Kīholo rain gauge. We are operating this in cooperation and funding from the State of Hawaii Commission of Water Resource Management. The station was established in 2002 and is located next to a previously monitored groundwater well that we operated for about 6 years. And as I mentioned before, while we are operating 2 independent data sets of precipitation data, only one of those data sets are publicly available, and the other is just used as a backup and an internal quality assurance check that we could switch over to if the primary rain gauge is starting to have issues. In this image, you'll see some of the other components of a typical gauging station. You have to have generally a 12-volt sealed lead acid battery, a solar panel for powering the equipment, an antenna, so you'll see in the background here, for transmitting that data back to our office. There's going to be a data collector, which again is just like a small computer that's recording that data and sending it out through the antenna through transmissions to satellites. And then, of course, that data collector and the battery have to be housed in some type of structure that we call a gauge house. That way it keeps everything dry inside. So this slide shows a couple of different examples of how our Kīholo rain gauge data is being used. Some USGS related research going on. The report on the right is used data from the Kīholo rain gauge to assess the intensity of rainfall that would generate runoff, and therefore the amount of water that dry wells on the west side of Big Island would have to accommodate. Dry wells are widely used on Big Island for disposal of stormwater runoff, and so the data from the rain gauge helped to create groundwater models that assess the potential for contaminants carried by stormwater runoff that may affect groundwater resources. Rain gauges are also an important part of groundwater recharge assessments that the USGS has performed across the state. And the Commission of Water Resource Management relies on these groundwater recharge estimates to manage groundwater usage. During the last assessment of groundwater recharge for the island of Hawaii in 2011, the Kīholo gauge unfortunately did not have enough years of data collection to help inform these estimates, but it will undoubtedly be used in future updates of these estimates, particularly given the importance and priority of the Kīholo aquifer for future monitoring. Some other examples is the National Weather Service used data from the rain gauge to aid in flood forecasting and issuing weather alerts. Data from the site will be useful for detecting potential trends in rainfall rates over time and for monitoring potential changes in the spatial distribution of rainfall across the state. And these, of course, are just a few examples of how the data is currently being used, but there are likely many more examples out there, opportunities of how this data is being used to help support other types of research, including improved tropical forest studies and management of the Puʻuwaʻawaʻa Forest Reserve. And so now I'm going to close out with just a few figures from the statewide monitoring needs report. The image on the left is showing anywhere there's orange shading is where some climate projections are indicating a decrease in future rainfall of up to 15% or more. And this includes the Kīholo aquifer area. So this taken into consideration with overall concerns about reductions in groundwater recharge caused by climate change and other factors and considerations that were discussed in further details in the report, resulted in identifying the Kīholo aquifer as a high priority area for monitoring, as there are currently no active long-term monitoring groundwater sites. So you see on the image on the right, anywhere with the red shading was identified as a high priority area for groundwater level monitoring. Our Kīholo rain gauge, being in one of those high priority areas, is therefore critical for informing rainfall and groundwater recharge estimates for that aquifer. And that is all I had. Are there any questions?
Awesome, thank you so much, Madison. And yeah, I said this in the beginning, if you have any questions, feel free to unmute yourself and turn on your cameras, or you can put them in the chat and I can read them to Madison. Thank you all for coming again. And yeah, that was very informative. Thank you, Madison.
And of course, my email's up there if any of you have follow-up questions that you want to send after this.
Yeah, and I will be sending that in the follow-up email as well, as well as the feedback form and the link that she was sharing earlier. And if nobody has questions, that's okay too. Okay, well, thank you so much everyone for coming. We can wrap it up and we can all unfortunately get back to our work days. Yeah, so thank you.
All right, now thank you, Olivia, and thank you everyone that was able to attend today.
Of course, see you next time.